Okay, so the example we're going to start off with is going to be, let's see. We're going to find the max and min of f of xy equal to 1 minus x squared minus y squared, subject to the constraint x plus y equals 1. So, for like real world problems, you'll only care about one, the maximum or the minimum, but this is just an abstract thing, so we can go ahead and find both. And I'm just going to note my f is 1 minus x squared minus y squared. My g is x plus y. And my c is 1. This thing where you're given the constraint and have to identify what your g is and what your constant is the only kind of like tricky interpretive part here. So I wanted to be really clear about what's happening. Here's our g of xy equal to some random number. And sometimes there's more than one way to pick g and the number. Like I could do, it would be silly, x plus y minus 1 for g is equal to 0. Goes to the same place. So don't worry, as long as you have g depends on x and y and the constant has no x or y, you're okay. And my gradients are going to be that grad f is minus 2x minus 2y, and grad g is just 1, 1. So if I want to set these two things equal, grad f equals lambda grad g, I'm going to have minus 2x minus 2y is equal to lambda times 1, 1. But we know that random numbers can go ahead and pop inside vectors, so that's equal to lambda, lambda. And so this is going to give me two equations because I can't combine the different components of my vector. That's going to give me minus 2x is equal to lambda, and minus 2y is equal to lambda. And my original equation still has to be true, that x plus y is equal to 1. So I have three equations with three unknowns. Let me go ahead and go back and label everything that we've done so far. So first, I made sure I understood what everything was. Then I went and computed my gradients. Then I set the two things equal to each other. And that gave me these first two equations. And then I went back to my constraint, and that gave me my last equation. And my next step is to solve these three equations for the three things I don't know, x, y, and lambda. And if I look here, I'm going to erase those numbers. They were so that we could talk about this, but now I want this space. If I look at these three equations, I'm going to try to think of the way to make my life as easy as possible. Okay. I'm going to label these 1, 2, and 3, my three equations. And first I have the minus 2x is equal to lambda. And I also have the minus 2y is equal to lambda. So minus 2y is equal to minus 2x. Or y is equal to x. Let me try to be really clear. First equation I solved for lambda. Then I plugged in lambda to my second equation. And I found out that that means y is equal to x. So I'm going to go over to my third equation. I'm going to say, okay, x plus y is equal to 1, but that means x plus x is equal to 1. So I replaced y with x. So I've got 2x is equal to 1 or x is equal to a half. If x is equal to a half, then I know that means y is equal to a half. Oh, y is equal to x is equal to a half. And I don't care what lambda is. I could solve for it at this point, but it's really not important to me. What matters to me is that the point 1/2 seems to satisfy my constraint and the condition to be a potential maximum or minimum of this function. Okay, so up to this point, what I've done is I've finished step 5, solve my system of equations for my points x, y, and lambda. And I'm only going to need x, y, so I just saved that value. But I also have to find points x, y that are on the boundary of g of x, y equal to c. So the constraint is x plus y is equal to 1. Oh gosh, I forgot to write down part of this. Sorry, the end of the problem said x and y are greater than 0. And I need to find the boundary of my constraint. So here's my x, here's my y, and I'm looking at y equals 1 minus x. So if I'm there, here's y greater than 0, here's x greater than 0. Here's the segment of the line, y plus x equals 1. So the endpoints of my boundary are going to occur kind of, the whole line segment is fine, except for when I suddenly end it right here. So if x is 0, then I know y is 1. That's this point right. Oops, that's this point right here. Let's give that a star. And if y is 0, x is 1. And that's this point right here. I gave it a little flower shape. Same as when we did absolute extrema, the process that we're solving is going to tell us about all the changes that can occur in this region. But you can imagine that if there was kind of like a general increase in the functions, we wouldn't catch it as a turning point. We need to evaluate where we cut off that point in case this is a maximum. Same deal here. So this gives us 2 points to consider. One where x is 0 and y is 1, and the point where x is 1 and y is 0. Along with the point we had before, 1/2, 1/2. And so we're going to evaluate f. Actually, let me just copy it real quick. F of xy equal to 1 minus x squared minus y squared. So f of 0, 1 is 1 minus 0 squared minus 1 squared is 0. F of 1 comma 0 is 1 minus 1 squared minus 0 squared is 0. And f of 1/2 comma 1/2 is 1 minus 1/2 squared minus 1/2 squared. That's 1 minus a fourth minus a fourth. 1 minus a half is just a half. So if I need y equal to 1 minus x, if I need x plus y equals 1, and I'm trying to maximize f of xy equal to 1 minus x squared minus y squared, that's going to happen at the point 1/2, 1/2. And the value of that maximum happens to be a half as well. If I'm trying to minimize it, that's going to happen at f of 0, 1 or f of 1, 0, and the value of that minimum is 0. And how are we doing on time? All right, we're a little long. Sorry about this. I just want to say, important to note, our constraint x plus y equals 1 shows up in the inputs. So 1/2 plus a half is 1, 0 plus 1 is 1, 1 plus 0 is 1. Our maximum slash minimum shows up where whatever f is equal to. So the biggest f can be when this constraint is satisfied is a half. The smallest it can be when this constraint is satisfied is 0. That's just the way to interpret the different parts of this result.